So let's get started. So welcome back, everyone. So today we're going to talk about support vector machines, kernels, and like how to generalize the basic techniques we learned in the first two lectures to nonlinear classifiers. We will see other types of nonlinear classifiers in the next lecture as well. Kind of like clustering, but also kind of very different. There are huge variety of ways you can learn a classifier, and we will review about some of those. It used to be that about 10 years ago, really the state of the art really went through types of like support vector machines, and that's kind of changed, and I'll kind of explain why that is. But what we can still learn from these sort of ideas. Just looking at the schedule, there are 3 lectures left, and this one has a quiz in it. Okay, so we will stop at, let's see, at 11:35 to give you time for the quiz, which will open then on. So Canvas, again, you get a cheat sheet. You haven't made that, so do it now. It'll be open until midnight or the end of the day, but I'll be around for at least for the first half an hour to definitely answer questions and so forth. Again, this quiz will be on all of clustering and the first 2 lectures on classification. I kind of wanted to check if there was any kind of particular questions people had about the material that's going to be covered on the quiz before we dive into the material for this lecture. I think some of the stuff we'll talk about, we'll kind of review some important aspects about classification, but we won't go over things about clustering, which will also be on the quiz. So great. So if there aren't any questions, I'm happy to go on with the lecture. We can cover a little bit more about kernels and such then. So great. So let's start by reviewing the Perceptron algorithm. All right, and so this algorithm, the input was x, y in RD cross -1, minus and plus. The goal is to find a classifier that is going to be matching these inputs, right? And so the output here is going to be W in RD, and so that W dot XI, if I look at this times YI, or that this is greater than 0, right? So that means that the sign of W dot XI is going to equal the sign of YI, right? So YI is including the sign. That's a class that we want to predict, and we want the signs to match, right, for the inner product of some vector W that we're learning. And so there's this important duality that the classifier is in RD and the data is also in RD. So these have the same form. So if you store them in a computer, they both are an array of size D, right? So you store them the same way. You can take a dot product between them. The identities match here. We assume that this goes through the origin. We can add an all ones kind of coordinate if we want to do that. And then the algorithm works fairly straightforward, that we start that W is equal to yi times xi for any xi, yi in xy, right? So I can start with any of these, and then I just so repeat, if there's any xi, so yi, so that if I look at this sign, xi w is less than 0, so this means it's a misclassifier, then I update w equals w plus yi xi. Again, I use the duality that these have the same form, w and xi, so I can add them together with the sign, right? And so this pushes it kind of in the right direction. Okay, and we showed last lecture that this, if we have a linear separator, if it's linearly separable, the data is, right? So that I have data that are pluses, these are the positive points and some negative points, then I can define a classifier, and this classifier goes through the origin, helps if you draw the origin afterwards, and it has a normal vector, w, that's pointing towards the positive points, right? The normal vector, in fact, you can think of coming out of the origin, but it's a vector. It's conceptually, it makes sense to look at anywhere there, right? And so if you recall, the margin was kind of this region to the closest point, gamma star would be the optimal margin, and if that's the optimal margin, then that determines how many steps I need of this algorithm. That's all I need in order to see if it classifies, if it's a classifier. Right. So, okay. So what we want to think about today is, what if it's not going to be linearly separable? What if it is not so linearly separable that I can't find a linear separator? Okay. So I'm going to think of an example now where I have some data points, and right. So this will be a nice example because it kind of is a one-dimensional problem now, and we'll look at this version of the one-dimensional problem, and we'll see how we can fix this. But the concept will work in high dimensions as well. Okay, so I have a data set like this where I cannot find a linear separator that kind of separates the red from the blue points. If I put it over here, well, then I've got a problem on kind of these points over here are a problem. If instead I try and put it on this side, well, then these points over here are a problem, right? So I can't really find a good linear separator that solves all the points here, okay? And so if I can't do this, I can't run the perceptron algorithm. And also I can't, I mean, even if I ran the gradient descent based algorithm, it's not gonna give a good answer either. That's gonna try and minimize how badly points are misclassified. It's gonna give a penalty to them, and it'll find something, but it's not gonna be very good, right? So yeah, so for instance, I could think of this problem as representing kind of the score on kind of so homework 8. I'll use homework 8 so you don't have worries about any of your actual homeworks. We don't have a homework 8, and I want to know, yeah. So it's minus, and yeah. So this coordinate is not so important, right? I only need one coordinate to show this example. There might be another coordinate, maybe quiz score on homework 7 or something, and I want to say that I get minus if student earns so B in the class, right? And so I want to say a plus if student earns not a B, right? Could be an A. Maybe these are A students, these are C students, and the ones in the middle here are the B students, right? So it seems like I should be able to find a good classifier here, but I can't do it with a linear classifier. Okay, so everything we've learned so far does not work here, but this seems like something I should be able to learn a pattern for, right? So the way, kind of a common way of approaching this is to generalize the notion of the inner product. So generalized inner products. Okay, and these we're gonna think of these as, so kernels is kind of a general way of doing this. Okay, so we typically had points P and X in our D, and we thought of the linear inner product, also known as the dot product, is P X again is equal to J equals 1 up to D of Pj times Xj, right? I just multiply the coordinates together and I add these up. This is our inner product we've been working with throughout the semester. I'm finally going to change the inner product here. After I've said this will be basically all we have to learn about. And we'll use it we'll replace it with the type of a kernel instead. Okay, and a kernel, kind of the most common thing people think about when they think of a kernel would be, so, one of the most things that keeps coming up in the course is the Gaussian kernel. All right, so this is a Gaussian kernel, right? And this looks at, we've seen the normal distribution, and the Gaussian is a multidimensional normal. And this says 2 points are similar to each other, not if the dot product is large, but they're similar if they're close in Euclidean distance, right? So I have a measure of Euclidean distance in the middle here with the norm, right? And then I divide it by sigma squared, right? This gives us a sense of scale. All of these have some kind of parameter like sigma scale. This isn't the only one. You could do Laplace kernel, which is X minus P. Now I don't square it or the sigma. And this is also another kernel. So it behaves in a very similar way. Sometimes it's more robust. Sometimes the Laplace one is a little bit better. Another common one that we'll talk more about is going to be the polynomial kernel, and this one is going to rely on the inner product again, P inner product X, but it's going to do plus some control parameter C, which will be greater than 0, and sometimes you just set this to 1 and R to some power R. Okay, this is a polynomial kernel. This is the typically called, if this is a Gaussian, this one is a so Laplace, and both of these are typically called RBF kernels. Usually people are referring to the first one, the Gaussian one, but this one is also a radial basis function kernel. It kind of radiates from a point. If I pick a point in the middle and I think of what I care about is these distances from the points, right? So it's this radial basis, and the value of the kernel at a point P is the distance from X to P. So there are kind of these concentric circles that determine how similar things are. Okay, so I want to use, so basically, I can think of these as generalizations of these inner products, right? So I'm going so I can write kind of Px kind of maybe G is equal to here, Px the Laplace is equal to here, and Px, and this would be kind of a polynomial is equal to this one, and maybe I specify the parameters as well. But I can think of these as generalizations of the idea of an inner product or like a dot product. Okay, and we'll see with the polynomial kernels, if I were to expand this, right, this is written as some inner product. Again, that's going to have a lot of terms in it, right? That's the same inner product here. So it's multiplying a bunch of factors together. And then I'm multiplying it by a constant c and taking it to a power. If I were to expand that polynomial, I'm going to get, because some of the terms are by constant and some not, I'm going to get kind of a lot of the aspects of the, I'm going to expand into like a polynomial with a bunch of coefficients. So it turns out I don't need necessarily to worry about all those coefficients if I do it this way, but we'll see, we'll look at that expansion later. So like we did polynomial regression, there's a way to think about polynomial SVMs through an expansion as well. So, but let's start by thinking about the kernel version, and then we'll look at the expansion version a bit. So later here. Okay, so think of, if I have the big concept here, and this is true not just in kind of nonlinear classification, which we're going to talk about, but this, a trick called the kernel trick is to look at an algorithm and look at all the places I use an inner product and replace it with a Gaussian kernel. Okay, this is called the kernel trick, and a lot of algorithms, including like regression and clustering and dimensional reduction, you can write them so the only way you interact between two data points is an inner product, and I just replace all those with the kernel, and then I get what's going to be a non-linear version of them. And we're going to work through that today with the Perceptron algorithm, and then once we understand that, which is a little bit conceptually, I think, a lot easier case to think through, we'll talk about generalizing it to like the gradient descent approach, and that one, it's often what's called like the support vector machine. Okay, although that name support vector machine can mean kind of several different things here. So great. Okay, so we're going to think of replacing this inner product here, defined by this linear dot product, instead with like this function, right? Or this function in its place. We're going to replace that in our algorithm. And I think this is a pretty simple change in the Perceptron algorithm, right? The Perceptron algorithm, well, yeah, oh yeah, there's one more, return W divided by the norm of W, but this won't be so important. That doesn't change the classifier at all. Okay, so we're going to try and replace it here, and there's only one place that it's showing up, right? It's only showing up in this check. We somehow need to replace it here, but we also need to replace this step, this update step, and that one's going to be a little bit trickier here. Okay. So our goal is to now yeah, so our goal is to learn yeah, so first I want to actually show why this can give a nonlinear classifier. Let me just show how it solves this problem first. Okay. So one way of thinking about this is that if we're going to use a polynomial so classifier where the x is going to be a subset of R, so just the real values, and y is still going to be in -1, +1 here. Okay, so I'm going to get a set of plus points, like in this example I showed before, and it's going to be non-separable by a linear classifier. Okay, so these are the positive and the negative points here, and this is just in one dimension, right? So I can think of this as being just one dimension here, and this is the value of xi. Okay, and so what we're going to do is we're going to do something. We're also going to look at xi squared, right? So I'm going to map every data point into a two-dimensional data point. Xi is going to map into qi, which is going to be xi squared. The same sort of trick we did with polynomial regression, and kind of using a kernel function to do something similar, but I can't make it quite as concrete as this example. Okay, so I can't get a linear separator in the original points, but now if I map these to some associated points with the squared, let's actually set the origin here, right? So this is xi equals 0. Okay, so I get xi equals 0 here, and so what that's going to do is that it's going to map all points onto a parabola. Okay, I'm mapping so every point that has the value xi and xi squared, it has to follow this pattern, right? I haven't added any information. I'm just going to change the representation of the points. And so now all of the plus points are now lifted up to this parabola. And it's going to be similar with the minus points here. And the beauty of this is now I can find a linear classifier. Okay, once I'm in this higher dimensional space, right, these are now the points Q, which are in RD, or in R2. Now I'm in R2, and I can define a linear classifier, right, that's going to be in this lifted space. So I'm kind of think of lifting these points to a higher dimensional space in some way which is a nonlinear mapping, right? It's based on this parabola in this case. Now I can find a linear classifier. Okay, so I haven't added any information. I've just changed the representation of the data, and I'm going to effectively change the representation of what the classifier can do as well. Okay, so in the polynomial case, I'd like to do this, but the Gaussian kernel case is actually probably slightly more common. Okay, so and to think about how I do that, in the case of the Perceptron algorithm, so let me kind of explain like a little bit more how this is going to work. So okay, so kernel. So Perceptron here. All right, so the key is that I'm going to change how I represent the classifier. And I'm going to represent it as a mistake cell counter. And I'm basically going to keep track of which points made a mistake, and I'm just going to keep those counters in it, right? So my W vector, I'm going to write this as I equals 1 to n times alpha I yi xi. Okay, where alpha is going to be alpha 1, alpha 2, up to alpha n, right? So this is going to be a vector in Rn where alpha I is equals to the number of updates with kind of xi, so yi, right? The number of times I added yi plus xi is going to be a value at alpha. So it's going to be a counter. Most of the values are going to be 0. Okay, this is going to be mostly alpha I is equal to 0. Most of the points, I probably won't make a mistake ever in the run of the perceptron algorithm. I know at most it's going to be at most 1 over gamma squared, gamma star squared. That's the most number of entries that I could have which are non-zero. So if n is very big, most of them are going to be non-zero, are actually going to be zeros. Okay, and the other ones are counting how many times I did an update. This should be the same representation I had before. This can be the same vector I had before. I'm just storing it in a slightly less efficient way. I could probably use a kind of a sparse vector representation and just store the counts. And maybe it doesn't save space, but let's not kind of worry too much about that so at this point. Okay, so ultimately what I'm going to want, right, is for so I'm going to want a predictor function which I want to use the sign of, right? So I want to use the sign of this function g of p. So I want this to match the sign, the sign of this function at a point p should match and for p is going to be an RD, right? Then this should match what the true sign of the point p is, right? And so remember, this was equal to WP. So if I want to make a prediction at P, then I just take the inner product with W here. Okay. Right. And W now I'm representing it this way. Instead of keeping track of a d-dimensional vector, I can actually represent it this way. And I can write this as sum I equals 1 to n alpha I, yi, xi, p, okay? All I've done is I've taken this redefinition as a mistake counter of W and I put it inside this inner product. And with inner products, I have this nice property. It's just, this is still the Euclidean dot product here. So I can just factor out a bunch of these terms, right? This is going to be equal to, I can move the sum outside as well as the scalar alpha I and yi, and what I'm left with is xi and p. Okay, so this is the same predictor function we had before. I've just rewritten it differently now. And now I've written explicitly as this, so mistake counter. Okay, so now I had this problem. I wanted to replace things in my kernel with in my Perceptron algorithm with this kernel, but I was doing these other steps where I'm adding vectors together. And I couldn't quite do that before, but if I do as a mistake counter, this should be fine. Now, the only place I'm using this inner product is to compare two data points. I'm not using this more complex thing where I'm keeping track of this vector, which is an aggregate of data points. I've kind of turned it into the sum of these effects of these data points. Okay, so I haven't changed anything except the representation. This is a different way of implementing the same algorithm. The same algorithm, but I've implemented it differently. I'm summing over the things I've made mistakes on instead of keeping track of a vector W. keeping track of the vector W only requires D space. And it's probably simpler if I think of it that way, but this way will allow me to generalize it to kernels. And so that's kind of the important thing I'm going to do here. And so now I can actually write this as I equals 1 to n alpha I wi of a kernel xi p. Okay, so now I can replace how I use the inner product with this kernel, and now I get a nonlinear classifier instead. Okay, so if we look back at the perceptron algorithm, okay, there are two steps where I potentially needed this inner product. Here, this is to check if I misclassified something. Okay, well, I'm going to replace this with it's with W, which is not a data point. But I can replace this with the sum over the mistake vectors. And instead of doing an update where I add a vector to the W, well, I just update my mistake counter. It's really updating a sum, right? I'm adding something to a sum. I just keep track of the mistake counter, and that updates kind of my representation. All right, so kind of the kernel perceptron okay, I'm basically going to set alpha equals to all zeros in Rn, and then I choose, say, alpha I, and I set this to 1, right? So now I have one thing in this mistake counter, okay? And then I do so repeat, yeah, this is for I somewhere in n. If sum x, y in my data set has if I do the sum over j equals 1 to n of alpha I, yi, inner product x, oh, these are j's, times xi. Okay, xi is the one in the data set, j is what this function is over. If this is less than 0, then I set alpha I equals alpha I plus 1. So I've updated, I said I've made another mistake at index I. I just update my mistake. Okay. And then I return a function which is going to be g of something, which is sum j equals 1 to n of alpha j, yj, inner product xj, dot. That's where I evaluate. So now this is my function. Okay, and now every time I did an inner product is between two of the objects, so I can replace this with k of xj, xi. And where this is k of x, xi dot. All right, and this is how I can build a nonlinear classifier. Yeah. Well, now I'm returning a function, and the function, I'll look at the sign of the function, right? Before, I represented that function by its parameters w, and implicitly that was going to be used for inside the dot product, right? That was kind of implicit before. That's how we just return the parameters. Now I'm going to give you the whole function, and I'm going to look at the sign of this function to make my prediction. Yeah.
So some
Yep. Yeah, so that's going to be fine. In fact, the y's, the yj's are going to, some of those are still going to be negative, right? These yj's here, some of those are going to be negative. So it says, well, the points which have a negative label, if I'm close to them, right, I want to give a weight which is a prediction which is more likely to be negative, right? And so that's exactly right. So I'm going to say how much, think of the kernel, when I'm using a Gaussian kernel, the right way to think about this, the way I like to think about it, is I'm going to have points which are negative and points which are so positive here. And remember, these are kind of emanating these weight functions. I'm saying I'm close. When am I close to these points, right? And similar with these, but these are going to give a negative weight if I'm close. And I'm going to take a weighted average over the evaluation I get, right? So if I have a point here, it's going to have some impact from this point. It's kind of close to that plus point, but it's much closer to this minus point. Okay, so I'm going to think of this. So I'm going to get a decision boundary here, which is going to kind of look like this. It's going to kind of go to the midpoint, then curve, and it can kind of curve through here depending on where it's closer, right? So between this kind of this horizontal line between this negative and plus point where the curve is, well, it's going to kind of hit the midpoint between the kind of curve. So I can think of two kernel density estimates, which are weighted averages of the positive and the negative points. So I have the red kernel density estimate, which tells me where there's density for the positive points, and sim for the negative points. And I'm going to subtract one from the other, right? And so where the effect is positive after the subtraction, I keep it as a positive sign, and where it's negative, I get a negative sign. Yeah. So is it kind of like doing k-means? So yeah, so I'm taking an average over these things, right? So that's where you're seeing that. That's a good intuition. There's a kind of way of thinking about it. I'm doing kind of like two means. Now, k-means, I don't have the labels. I don't have the positive and negative labels. But there's a way of thinking about it. There's a way to think about Gaussian kernels in a high dimensional space. In fact, an infinite dimensional function space. Okay, but it acts Euclidean once I'm in that space. And effectively what I'm doing is I'm taking a mean of the positive points in that space and a mean of the negative points in that space. And the decision boundary is going to basically, I think, is going to be the, assuming the weights are equal, is going to be the bisector of those two means in this high dimensional reproducing kernel Hilbert space. I think that's an accurate way of thinking about it. So it's kind of like doing that, and that tells you which cluster you're in. But you have labels here. The k-means, we don't have labels. We're trying to kind of say, are there groups that would probably suggest a label separately? But this one, I have labels, and I'm using that to determine where the decision boundary is here. But I'm kind of like an average. So that's a good observation. Averaging happens a lot. Kind of central limit theorem, all predicated on averaging, so the more data I get, the better my estimate of where the decision boundary is. Yeah. Okay, so kind of converting this into a kind of a nonlinear classifier is a pretty simple and small change here, right? Once you think of it as this mistake counter. It's not necessarily more compact representation. I'm storing n-dimensional vector instead of a d-dimensional vector. N typically much bigger than d, but it kind of the algorithm is still pretty simple here. Okay, so this is a kernel perceptron. If I set kind of the bandwidth, the sigma value of the kernel small enough, and there are never 2 points directly on top of each other, I can always find a perfect separator now. Okay, I will actually always be able to find something. If I set the bandwidth small enough, it's saying, well, when I'm saying a point is nearby, right, the effect of it is decaying exponentially. And so I don't get, when I set the bandwidth small, my region around a point where I have a lot of information becomes very small, and it becomes not very so robust. Okay, so there was this parameter here, right, this sigma squared, or the sigma in the Laplace, and as I set that smaller, that says what is close, right? So you can think of this distance as being roughly kind of, sigma is about 1 standard deviation out, and after that it's decaying exponentially. So if I set that small, I can always find, actually always find a separator. There's always going to be a way to find a linear separator, but it's not going to be as robust to new data. Or not a linear separator, but a separator, which means the perceptron algorithm will always work. It'll eventually converge, but the margin might be small, so it might take a lot of steps to actually refine it, to get it so you get the right 2 kernel density estimates that balance just right. Whereas if there's a pretty clear thing, you know, if it looks like this example, it'll converge, or other data points, but these are the important ones, it'll converge pretty quick. And similarly with the degree of the polynomial, right? The degree of the polynomial here, if I set this guy large enough, I will always be able to find a separator. Again, it requires, it's a more complex function, and I typically don't want to do that. It might overfit. Overfit might be a way of thinking about the data. Although sometimes you actually want to do this, like we talked about with this. We had this extra lecture. We talked about like this, so double descent with cross validation. If I set either sigma small or r large, then I could use cross validation. Again, this is a supervised problem. I can cross validate to choose a good value there. And typically you want it to be just big enough to fit the data, not bigger than, or for r, or just small enough to get a good classifier quickly with sigma, but not bigger than that. That's typically the right way. But if I have way, way more data than I need, I can actually, you know, set these differently, and I can still, and I might start fitting well to my model again. Okay, so there's, okay, but I can choose those with cross validation now by holding out some of the test data from my training set and evaluate how well this works. Okay. Yeah, I talked a little bit about feature expansion, but let's go back to this just for a minute. And let me give another example. Let's say that a data point, yeah, to distinguish, so I don't have to deal with indexes much. Let's say this is a data point. And I can think of it as 2 coordinates, x and let's say z, just to distinguish it from y. Okay, if I want to do I can also do a polynomial expansion. Okay, and so what this will do is it'll give me another data point. If I have 2 coordinates, right? We didn't quite talk about this with 2 coordinates before, but I'm going to get kind of just x. So I'm going to have alphas, could be alpha 0, or maybe I do alpha 0 plus alpha 1 x plus alpha 2 x squared plus alpha 3 z plus alpha 4 z squared. And then I also need one more to get a second order expansion. which would be alpha 5, which would be x times z. So I want to, typically you want to get all of these here. So now my model is going to be by an alpha vector that's in R6 is this expansion. Okay, so in general, so I want to consider all polynomial terms where the total degree is going to be at most 2 or at most p, right? So so if I want to go to at most, so as I'm increasing the terms of the polynomial, right? So at most, if I want degree r, I'm going to go to some dimension of q is going to be O of d to the r. So it's going to roughly grow exponential with the degree of the polynomial. So this gets pretty high dimensional pretty quickly if I do this expansion. So if I want a higher degree polynomial, you typically will just use this kernel approach, and that will be less cumbersome than expanding this. But once I've done this, I get kind of just a linear model again. And so doing this will also give me a nonlinear classifier. I can now run on my data set after it's been expanded to RD, and now I find a linear classifier in that space, and that's one way, you know, I get a picture that looks like this. I get now my classifier here, you know, W is now in our R2 instead of R1, or in general this R, you know, D to the R, you know, that's what my dimension is going to be, and I can represent it this way by doing this polynomial expansion. This is also so then the inner product, you know, the generalization inner product between some x and, let's say, so W here, okay, and let's say for R is going to be equal to so I would have I do this expansion of 1x squared z squared x z. So I have a 6-dimensional vector, and I have this this alpha vector, or this might be the same as W, right, as the inner product, right? But now this is a linear inner product once I've done this data conversion, and I can use this as my generalized kernel as well. Okay, so this is another way to kind of explicitly get these nonlinear classifiers. Again, hopefully this is not too new or ideas. We did this a lot with polynomial regression, but you can do the same trick here as well. There are kind of ways to do this with like the Gaussian kernels, but as I was kind of alluding to with your the answer to your clustering question is that the expansion you would need for a Gaussian kernel or a Laplace kernel to do this is actually going to be an infinite dimensional expansion. So I need an infinite number of, I can do that. There are ways of doing like a Taylor expansion. There are ways that approximate it, where you can get to like, if you use like roughly 100 or more dimensions, it gives a pretty good approximation that's unbiased. And so some people use those, and that shows up in some settings that's easier than the kernel trick. But it's, yeah. So you can kind of do it for the Gaussian stuff, but it's kind of, it's messier. Okay, I want to, okay, I did not get to talk about SVMs. SVMs, I'm going to say, is once I've kind of got this representation with the mistake counter, but then I'm going to run gradient descent, or I'm going to identify ways. So if I run stochastic gradient descent, you know, I'm kind of identifying a subset of the points which are going to be non-zero, and those will be the support vectors. Let's talk about that a little bit on next week, Tuesday instead. And instead of jumping into that, but that's kind of the main idea. And all right, we'll stop here for the quiz, which should now be open on Canvas. And then we'll do kind of a potpourri of other nonlinear things, including neural nets, on the lecture on Tuesday.